What we'll talk about today is the following results. So suppose that you have sets A, B, and C. Of unitary matrices, and the measure of them is at least e to the minus c and to the 1/3. So the sets could be quite tiny. And then we get that if we choose randomly A from A, which you can interpret as choosing A out of the hard measure and conditioning that this A is in A, and then choose B from B, then the probability that A, B is in C is close to its measure. So it's equal to the right thing up to a factor of 1.1. That's the theorem.
Is it 11 or 1.1?
1.1.
Yeah, that's the point. Sorry, does the 0.9 and 1.1 depend on the C in the...
Yeah, so if you want to make them smaller, you can make it smaller.
Okay.
I mean, yeah, it's the measure up to a small multiplicative factor. Okay, so that's and this can be represented analytically. So if we take F to be the indicator of A and G to be the indicator of B, then we can restate it analytically. And so we can define the convolution of two functions by the expectation of over y of fy gy inverse x and x. Okay, and then this thing just says that if you take the convolution of f with g and take inner product with h, then this thing is close to the product of the expectations. Okay, so is the internal. And so what? Okay, and Gowers he proved something similar when but when the sets are larger. So okay, so when the measure is at least n to the minus 1/3,
Okay.
And basically, it turned out that Sarnak and Choi proved something similar in a different context of automorphic form, the spectral theory of automorphic forms. And Gowers, when he proved this result, he introduced this notion of, so this was in 1991, and this was in 2006. And basically both use the following notion. Okay, so a group G is equal to random and for every representation, which is a homomorphism, from G to invertible matrices and d minus 1 by d minus 1 invertible matrices, for every such homomorphism, rho is always equal to the identity matrix. So rho of G is always the identity for all. So this means that the group doesn't have small, so each such thing is called the representation of dimension d minus 1. And basically, this notion tells you that the group doesn't contain a representation of dimension less than d. And we know that if G is abelian, it has homomorphism to the tau, so it has lots of one-dimensional representations. And this notion is about being the opposite of abelian. It means that all the representations have large dimensions. Okay, I'll try this. Also, if the other board okay, should every time you learn a new trick, you forget the old tricks. Okay. Right. So, okay, so that's the notion of a quasi-random group. And what Sarnak and Choi proved? Was the following. So suppose that f and g are functions from a group and that g is quasi-random. Then you get the following remarkable property. If you take the convolution of f and g, it's close to the product of the expectation. this is bounded by 2 norm of F times the 2 norm of G divided by root D. Maybe I should write it. No, I don't know. In case you can't see this. Okay, so here you have, when you take the convolution, you have the product of two random variables. You have f of y and g of y inverse x. And these random variables, y and y inverse x, are very correlated. The product is always equal to y. But even though they are correlated, the expectation of the product is very close to the product of the expectations. So that's why somehow it's called the quasi-random group, because if you take two elements that you know the product, somehow it doesn't tell you anything about them individually. So let me tell you why this thing is true. Okay, so you can define an operator Tf, where Tf of G is defined to be F convolution G. And we want to show that, we want to prove a bound on the operator norm of Tf. So the goal is to show that if we take Tf and upper bound and its operator norm on functions in L2 that have expectation 0, then we want to show that this thing is most the 2 norm of F divided by root D. Okay. Right, because we want to show that if G has expectation 0, then we can get this bound. This is a bound of the operator norm of this convolution operator. I don't know if we should say that this thing is functions in L2 that have expectation 0.
Isn't that exactly what is written?
Yeah, so this is, yeah.
It's just another way to write the same thing.
Yeah, okay. And so the operator norm is, you can look at now at Tf star Tf, and you want to upper bound its maximal eigenvalue. Yeah, maybe it's better to assume that F has expectation 0. Okay, and then, yeah, so basically we want to upper bound the maximal eigenvalue. This thing is the square root of this thing, the maximal eigenvalue. And it turns out that the trace of Tf star Tf, this equals to the L2 norm of F squared. it's easy to convince yourself that that's true when G is finite. And so F corresponds to this random walk where you move by a random element from a set, let's say, and then you do the opposite random walk. The probability that you return to the same place is 1 over the size of the set. I mean, this is an exercise when G is finite, at least. Okay, so we can always upper bound the maximal eigenvalue by the trace. But when you have symmetry, like in this case, you actually can do something better. Okay, so if we define this operator RG, corresponds to multiplication by G from the right. So RG of H is H of X. Then RG and TF commute. Because the convolution corresponds to multiplication from the left. So it commutes with multiplication from the right. But this means that each eigenspace, and the same is true for Tx star Tf. So you get that each eigenspace of Tx star Tf it satisfies the RG of V. So all of these spaces, because RG commutes with Tx star Tf, they must be invariant under RG. But this gives us a homomorphism, a representation that we can send G. We can define rho of G to be RG. And what we get here is that, so either so either the dimension of V is at least D, right? So if the dimension is at least D, then we're happy, because then we get much better bound when we compare the maximal eigenvalue with the trace. Or if the dimension is smaller, we get a homomorphism to GLV. So we get that rho of G must be the identity for each G.
In the first case, you get better bound for V being an eigenspace of the maximal eigenvalue.
Yeah. Yes, you take a.
So you get that the maximal eigenvalue appears at least D times, and therefore the trace can be divided by D, and it still bounds the eigenvalue.
Exactly. Yeah, so. Yeah. Maybe we should write it down. So if dim V, let's say dim V lambda, the eigenspace for the eigenvalue lambda is at least D. Then we get that so lambda, the spectrum of T star TF. Then we can say that d times lambda is smaller than the trace of T star TF. Which is the norm squared. So you get that lambda is at most, which is what we want, because it means that every eigenvalue can be ordered by this. And otherwise, rho is a homomorphism from G to GLP, and DV is smaller than D. So we get that rho of G is the identity. But this means that for every f in V, we get that f of xg is equal to f of x for all g and g. But this means that f is constant. So this can't be if we are inside the space of functions of expectation 0.
But sorry, this f is not that f.
Yeah, population distance. Yeah, let's call it h. So and probably g is also a bad notation. But anyways, if the dimension is small enough, then if the dimension is small, then you're invariant under multiplication from the right by every element of G, so you have to be constant. But if you convolve a function of expectation 0 with a constant function, you get 0. So this completes the proof. Okay, so are there any questions about this? Right, so we have the trace of TF star TF, it's the L2 norm of F squared. And we can add each eigenvalue, we put that each eigenvalue as multiplicity at least D, because otherwise F must be constant. Every eigenfunction that has multiplicity, every eigenvalue with multiplicity less than D, all the eigenfunctions there are constant. So this means that, so we get the trace is this thing, and each eigenvalue must be bounded by that number, and then we get the operator norm of TF is the square root of the maximal eigenvalue of TF star TF, and then we get the bound. So I'll move on. And it turns out that SUN is n times random. So you always have the representation that's the identity, since each matrix to itself, it's of dimension n, and it turns out that this is the minimal dimensional representation. Okay, and let's also, so now let's recall stuff from last lecture. So,
Is this an easy fact?
this thing.
Standard fact.
Okay. I'll think about it whether I have a simple argument for it. But it's known for a while.
No, but you should say, like, this is what representation theories do. They classify all the representations. So
When they're successful.
not like if one analysis is something new.
Yeah.
The representation theory of SUN has been studied for a very, very long time. It's extremely important for quantum physics. So whether or not it's a simple fact is another question, but it's well known for a long time.
Sometimes you can give like easy arguments that know about the dimensions.
Probably.
And it's probably not the right time to think about such a okay, so. Right, so SUN is quasi-random, and we want to say that okay, we can somehow do something better. It's going to be related to the level D inequality. So we said that if we look at a Boolean function, so if we have a Boolean function of expectation epsilon, then if we sum the Fourier coefficients at level D, then this is at most epsilon squared. Okay, give it a simplified version, go to the D1 over epsilon. So there is an extra factor of D to the D. Let's just write it like that for now. This statement is also true. Okay. And basically, morally, it says that the Fourier mass of Boolean functions of small expectation is concentrated on the high degree. And what we want to say in SUN is something similar, that even though we have small dimensional representations, we have the representation of dimension n, there is a similar phenomenon that all the Fourier mass is going to be concentrated on the high dimensional representations, the high degrees. And it turns out that in the Boolean cube, high degrees can also be interpreted as high dimensional representations. So in the Boolean cube, you can it's an abelian group, so it's a space of functions over an abelian group, but actually it's a representation of a non-abelian group, and you have the action of Sn, semi-direct product of Z mod 2 to the n. So you have the action of the abelian group by translations, and you also have the action of Sn by commuting the coordinates.
Also called the hyper-octahedral group.
Yeah, this is, yeah. Okay, so we have this action of this hyper-octahedral group onto the space of functions on the Boolean cube. And this space, you can, what we like to do is decompose it into basically eigenspaces of the noise operator. The noise operator commutes with this action. And so what will be is the space of homogeneous. Okay, so let's just write in the span of chi S, where S is equal to B. So B is the space of homogeneous polynomials with degree D. This decomposition is a decomposition into irreducible representations. So every space here is invariant under the action of the symmetric group, and there is no smaller subspace that's invariant under the action of the group. This means that this is the decomposition of the space into irreducible representations. And the high degrees, they correspond to the high dimensional representation.
So commutation one coefficient on the variable. Right?
Yeah.
And what is?
And Zimutu to then comes by translation. By translation, yes. If you view it back as 0, 1 to them. Yes, so the point here is that high degrees, yes, and also I guess the dimension of VD is n choose D. And this goes rapidly with P. So somehow the high degrees, they correspond to high dimensional representations. And the level D inequality tells us that all the Fourier mass is concentrated on the high dimensional representations. And this is what we're going to do to improve over this Sarnak Schwer, because even though SUN is n quasi-random and it has representation of dimension n, most of the Fourier mass is concentrated on the representations that are much larger. And then orbits. So how do you how do you define even the degree decomposition in SUN? Turns out that it doesn't involve a complicated representation theory to define it. You can just do the obvious thing. So, let's say the degree of a function f on SUN. So not every function is a polynomial, but if it's a polynomial, its degree as a polynomial in the entries. And their conjugates. So what we can do is, for example, you have the map that sends a matrix to the real part of A11 times the imaginary part of A12, and adds to it the real part of A22. Okay, so this is of degree 2. So the trace is a degree 1 function, but yeah, so this is not conjugation invariant. Every function, you can take any polynomial of degree D in the entries and their conjugates. And this is a notion of a degree. And then we can define the space B at most B to be the space of functions of degree at most B. So the space of polynomials of degree at most D. And then we can define B equal to D. Okay, so we want the analog of homogeneous polynomials of degree D. Here we just take the polynomials of degree at most D and intersect it and take its intersection with the orthogonal complement of functions of degree D minus 1. And then we have a decomposition of L2 of SUN and the sum of these spaces. And this decomposition, it respects the group action, because if you take a polynomial of degree D and you multiply it from the left or from the right, then you still get a polynomial of degree D. But these spaces are not irreducible. It's a decomposition that respects the action of the group, but it's not the finest decomposition. But it turns out that you can prove analogs of the results in the Boolean setting. So first, what we prove is an analog of the level D inequality. So suppose that we have a function from SUN to 0, 1. Expectation epsilon. And for some technical reasons, we need D to be at most with N. But doesn't matter too much. Then you get that if you take the projection of f, the L2 projection of f on the space B equal to D, and you take the L2 norm square of that, then this is at most epsilon squared times log to the D of 1 over epsilon. We can also get the extra D to the D factor. I just wanted to simplify the statement. Okay. So again, we get that the Fourier spectrum is concentrated on the high degrees. And you also have a relationship between high degrees and high dimension. Okay, so every every sub-representation
No, somehow now there is no connection between D and epsilon, like we have. So
yes, so I removed the hypothesis that D is at most log 1 over epsilon, and I made the statement weaker, so it becomes trivial when D is like 1 over. But it's true with, we proved the analog statement with D at most log 1 over epsilon, and the extra D to the D factor. Just wanted to simplify a little bit the statement while it's still correct. Okay, and the other result is that every sub-representation of B equal to D, it has dimension so earlier we had these eigenspaces with dimension was at least some number, so now this number is at least Cn plus D over D to the D. So when D is small, you get Cn over D to the D, and when D is large, it behaves like D to the M.
This goes all the way to like n squared, or how big can D get?
This is for all the
So the representation of like any degree?
yeah.
Sub-representation just means a subspace that is invariant under
The group action, yeah. Yeah, so basically, you can look at the same proof as before, and earlier we had these eigenspaces that are subspaces of L to 0. Now these eigenspaces must be subspaces of V equal to D for some D, turns out. And these spaces must have at least Cn plus D over D, the D dimension. Okay, so again we get that So basically we get the same facts. The first, the dimensions grow rapidly with D. And then, but the Fourier mass is concentrated on the high degrees. If we now set f equal to d to be the projection of f onto d equal to d, we can show that not too hard to show that f convolution g inner product with h is equal to the sum of f equal to d convolution g equal to d inner product with h equal to d. And now, and if we look at f convolution g inner product with h minus,
So you mean just sum? Or
Yeah, it's just sum, it's not the
just sum?
sigma.
sorry, yeah. Okay. And if you take, so if you look at d equal to 0, then you just get the product of the expectations. And this is at most the sum from d equal to 1 to infinity of that thing. And using a Sarnak way, it turns out that now you can upper bound it by f equal to d 2 norm, g equal to d 2 norm, h equal to d 2 norm. So Sarnak and Cauchy-Schwarz divided by root qd. Now I'm going to define it. There is a comma.
Are you going to sum over there or?
Yeah, there's some.
Sum will be from 1 to infinity. Yeah, so the above thing is like in the abelian setting when you have when you convolve, you get a product of the Fourier coefficients. Here you don't have the product of the Fourier coefficients, but you, instead of convolving the whole function, it's sufficient to convolve the chunks that respect the group action. You get somehow that the cost terms die, and you only get these f equal to d convolution. What's QD? And QD, okay, well, QD is the minimal dimension of the sub-representation of the equation. Okay. Okay, now theorem 1 tells us that QD is at least Cn plus d over d to the d. And theorem 2 tells us an upper bound for f equal to d. And now we see that it's important that we get an upper bound for the L2 norm of f equal to d that's close to the expectation. It's not sufficient to get some power of the expectation. We really want to get something as close to the expectation as possible. So here we get that this is at most. Yes, so the expectation of f times logarithmic factors. And we get that the logarithmic factors. So we have the logarithmic factors that fight this n over d to the d. And that's why we get the exponential bounds. Okay, so how do we prove this level D inequality? It's again by proving a hypercontractive statement. And we have actually two proofs. One works for the larger than root n, but gives you bounds that are less sharp. And one that works for the smaller than root n. It gives you the right bounds. So I'll tell you about again both of them. So first proof. The idea is to use so first proof, it uses the Fourier-Entropy-Influence theorem.
Will be the proof of what?
Of hypercontractivity.
Level inequality.
Of hypercontractivity, which implies the level inequality. Okay, I can say, okay, maybe I should formalize the statement with a hypercontractive statement. And maybe it's a good idea.
So level G is just theorem 2 over there, right?
Yeah. No, theorem 1. Theorem 2 is a low bounded.
No, on this blend, but
You have two theorem two.
yeah, you have two theorems too.
Theorem 2 on the lower blackboard.
Okay.
So that's the level inequality, and it's basically the same as in the Boolean cube.
Yeah.
And in the Boolean cube, you got it from the hypercontractive inequality, and here you also get it from the hypercontractive inequality.
Okay, so yeah, here there are two theorems basically about two different operators, but they both can be called hypercontractive inequalities. Okay, so one is that there exists a family of operators let's call it T delta, case such that if delta is smaller than square root q minus 1 over q minus 1, then the delta f and q is smaller than the LP norm of f. Okay, but now I didn't say anything because the delta could be the expectation, and then it would obviously satisfy it. But what we want is that to make it meaningful is some lower bound on the eigenvalues of this operator. So now we have two versions. So version 1. Okay, so each this is actually both versions. But okay, each eigenspace. And yeah, over here. Okay, so they all have a joint, and each eigenspace of T delta is contained
This applies on L2 SUN or?
yeah. Yeah. On SUN such that we get this thing, this hypercontractive bound. Each eigenspace of T delta is contained in some space V equal to D. And the eigenvalue is at least, so in the first version, the eigenvalue is at least delta to O of D. And for all of it, yeah, maybe we'll actually edit for the at most, and I don't know. And in the second version, we get it with at least delta to the D times C to the D for delta close to root n. For the utmost root n. So that's why we have the root n there. And this basically gives you, it tells you that you have the right eigenvalues up to the C to the D factor. That doesn't matter too much. I mean, it would be great to get like bound here.
So both statements are true of the same T delta, or
Oh, no,
change T delta? Okay.
Yeah. One is true with, okay, so this version is, you take the Laplace Beltrami operator and you take heat kernel for it. And this uses lower bounds in the Ricci curvature of SUN. And the second one is using a coupling approach that I will tell you about. It's interesting to get to improve on this the utmost root n.
Is root of a sharp threshold here? Is the square root of a sharp threshold for the version 2?
The version 2, no, there it could be that it's, yeah, so I'll tell you, this looks like a failure of our approach. Probably it's better to, it works up to the, up to linear in. Yeah, but let me tell you about this coupling approach. And the coupling approach is quite nice. You get hypercontractivity for free for this. So we define a family of operators T delta, and we don't really have to work to show that they are hypercontractive, because this would work for free. We only have to work to compute their spectrum, and then to show this part. This is the hardest part of the theorem. And to show that they are hypercontractive is quite easy. Okay. Okay, so what we do is we take the space of complex n by n matrices. Okay, so yeah, so gamma is
2n by n?
yeah, because it's complex n by n matrices. And yeah, so I mean, yeah, let's see. Okay, so we have a complex n by n matrix, and then you choose the real part and the imaginary part, independently according from the normal distribution. What do you do usually? You write something like this, right? But there are too many matrices. Okay. Yeah. Okay, but you take a complex matrix by choosing the real part and the imaginary part of each entry independently out of the normal distribution. Okay. And then you have a matrix, and you want to get a unitary matrix. So what you can do is just apply Gram-Schmidt on the columns. Okay, so given A, you can get a column in S1 by applying Gram-Schmidt on the columns. So the first column is going to be the normalization. The first column of A column is going to be the normalization of the first column of A by its length, and then and so on. Okay, now you can define an operator T from it starts from SUN and goes to the space of a complex n by n matrices with the normal distribution. And the operator is going to be defined by Tf of A is going to be equal to F A column. And you also have the adjoint operator T star that goes in the other direction, and basically given a function here. Yes, so T star.
Now again, what is A called?
A column. Okay, so let's say that A is equal to E1 up to En. So what you do is you normalize the first column, and then you
A call is what you get from the columns of A by applying the Gram-Schmidt
process. So you make E2 orthogonal to the first column and then normalize and so on.
But A is the unitary matrix, no?
No, so you start with a complex matrix here. So A is in Cn times n gamma, and then
It's
you
a way to get from a general
Okay,
matrix
okay.
into a unitary
Okay,
matrix.
okay.
Yeah, so you start with a matrix with random elements, then you get a unitary matrix. And it turns out that you do get a random unitary matrix because it's easy to see that this distribution is invariant under multiplication from the left. Once it's invariant under multiplication from the left, it must be the Haar measure. So you get a coupling between Gaussian space and SUN. And then you have the operator T star f of A, which is, you can write it as the expectation of f of B conditioned on B equal to A. So you're conditioning on an event that happens with probability 0, but yeah. And this is, you can take this as the definition of conditional expectation. Okay, and now what you can do is to define the operator T delta, and I added tilde because this is not, because you have to modify it a little bit. But you can find T delta to be T times U delta times T.
Is that fine, U delta?
Yes, so U delta is the noise operator in Gaussian space. Okay, so in Gaussian space there is a similar noise operator with similar eigenvalues and similar hypercontraction properties, and you can take this to be the composition. But because yes, so T, it preserves measures. T star is an averaging operator, so we get automatically. Yes, so in Gaussian space we have the theorem that if delta is at most square root of p minus 1 over p minus 1, then U delta FQ is at most FP. So you can automatically deduce that a similar theorem in SUN that for the same delta T star U delta T FQ, T star is an averaging operator, so this is at most U delta TF Q. And now this lives in Gaussian space, so we can say that this is at most TF P. And finally, we can say that this is equal actually to delta normalized. Okay. So yeah, I guess that's an immediate corollary. So basically, once you have a coupling between spaces and hypercontractivity theorem in one space, you immediately can lift it to a hypercontractivity result in the other space by doing this trick of.
But is it clear that this T star work from a peak to a P or Q?
Yeah, so
With no.
because it corresponds to a measure preserving. So if you start with a random A here, A call is random in SUM. So that's why T preserves LP norms. And T star is an averaging operator. So by Jensen's inequality, it can only.
Practically obvious.
So all you need from this coupling is that it behaves nicely with a measure.
Yeah. Yeah, so basically, yeah, if you have a space that resembles another space, and one of them you have hypercontractivity, you can couple it. You can couple two spaces and get hypercontractivity for free. But the only question is what is this operator, whether it has nice spectral properties.
Now maybe you should.
Right, okay.
We should.
Just stop it.
Let's think.